In this last section, we'll look at practical considerations for the implementation of numerical methods, including how to apply them in MATLAB. There are four main considerations that you need to take into account with any numerical algorithm. Those are convergence, stability, explicitness versus implicitness, and accuracy. Now, in the case of convergence, any good numerical method will approach a numerical solution as the time interval delta t gets smaller. What does that look like? Well, let's take a sample dynamic response. Let's say that this curve here is our analytical solution, assuming we can find one. If we use a large delta t, you may expect some fluctuations around the true solution. On the other hand, with a small delta t, we would expect these fluctuations to be much smaller. And as the delta t approaches 0, we would expect it to approach the analytical solution. In the case of stability, it is important to consider that some algorithms will simply blow up if delta t gets too large. So there is typically a threshold for each algorithm below which you will get a stable solution. For example, for Newmark's linear acceleration, the ratio delta t over Tn, the natural period, must be less than or equal to 0.551 for the algorithm to be stable. In the case of the constant average method, this condition becomes less than infinity. In other words, the algorithm will never be unstable. This is what we call an unconditionally stable algorithm. Now, the explicit versus implicit consideration has to do with computational time. If you recall, Newmark's method was explicit for linear systems, but had to be implicit for nonlinear systems. This means that it had to iterate at each time step to obtain a convergent solution. On the other hand, the Runge-Kutta method was explicit for both linear and nonlinear systems. This means we expect Runge-Kutta to be a much more computationally efficient algorithm for nonlinear systems. And finally, the accuracy consideration is perhaps the most important. This really trumps both convergence and stability, but essentially says a similar thing. As delta t gets smaller, the algorithm should become more accurate. And there's a few ways to measure that accuracy. Let's again take a look at what an analytical solution would look like and possible deviations from accuracy. One of these is that the period could elongate or shorten. This is what we call period elongation. You could also have a solution that decays over time. This is what we call amplitude decay. And it's something that can happen with certain numerical methods. And one good way to measure the overall error is to use what we call the mean squared error, or MSE. And that is defined as the mean of the squared difference between some true solution and the numerical solution. So let's use MATLAB to look at how some of these numerical methods compare to an analytical solution. So the first thing I'm doing is defining a simple dynamic system with a natural frequency of 4 pi and a damping of 20%. I'm also going to define a loading function with a loading frequency of pi and a magnitude of 3. And I'm using the anonymous function to create this function p, which I can call for any range of time t. But essentially this is a sinusoidal loading function. So I'm going to run this section and generate those parameters. Next, I'm going to generate an analytical solution for this system and loading. So I've provided you with this function sdof harm response. This simulates the harmonic response of a system given these parameters. We can take a quick look here. It takes as inputs the mass, stiffness, and damping of a system, plus the input forcing magnitude and input forcing frequency, as well as a time vector to solve for and some initial conditions. So this takes in everything we learned from Unit 2. So I recommend that you look through this and see how it's been implemented. Now going back to the main program, we are going to call this function. Instead of mass and stiffness, I'm just taking directly the system parameters. So I'm assuming a mass of 1, a stiffness of omega n squared, and so on. So I'll go ahead and run this, and that will generate our analytical solution, which I am calling U sub an. Now we get to the meat of the program. This is where we run various numerical solutions for a list of various step sizes. So this is the list of step sizes dt list. I'm going to start with a pretty big time interval or step size of 0.5 seconds, and I'll go progressively down to an interval of 0.025 seconds. Now let's take a look into this loop. I'm going to first draw my time interval from the list, generate a time vector, call that forcing function so that I have an actual vector for the loading function, and then I will run 3 numerical algorithms. First is the interpolation, for which I've also given you a program. Notice that this takes in also the mass, stiffness, and damping for the system, as well as a loading vector, some time interval, and some initial conditions. Again, I encourage you to look at how it's implemented and how that reflects in the algorithm that we presented in the 5.2. I'm also running a Numerical method, which is using the average variation, and a Numerical method which uses the linear variation. Now this is the same function, but I haven't provided it to you, as you will need to make this function for your homework. I encourage you to take this opportunity to make it and run this example with it as well. And in this code here, I am doing a mean squared error calculation. Notice that I rerun the analytical solution, this time using the time vector, which corresponds to the numerical solutions. That way my response points line up in time. And then I am using the same calculation for each to obtain the mean squared error. So let's run this and see what it looks like. And so the first thing we notice is that for our very large time step, one of our functions goes completely bonkers. So here we notice that the numerical linear method essentially blows up. If we were to extend this out more time, you would see it keep increasing. This is a key indication of instability. Remember that numerical linear method was one of the methods that could become unstable if the time interval became too large. That is exactly what is happening here. The interpolation and numerical average schemes don't seem to blow up, so we can assume that they are stable. However, the values of the unstable response become so large that it's very difficult to see what is going on in the others. But let's move on to the next time step, 0.25 seconds. Now we see that all algorithms are in fact stable. We do see a tiny bit of decay. In other words, our solutions are slightly below the analytical solution. Particularly the interpolation solution. Also in the transient period, we see a lot more error, and this is pretty common for these numerical solutions. As we increase the time interval to 0.1, we start to see much better results. Okay, so pretty good agreement between the responses. Maybe a tiny bit of error here still in the transient response time. And by the time we get to 0.025, the responses are tracking very well with the analytical solution. So it seems that the time interval around 0.25 is a good choice for this type of system. If you don't have an analytical solution, which was probably most of the time, what you would need to do is do some sort of convergence analysis. So decrease the time interval until you see very little changes in your obtained response. Now let's move forward. Notice I didn't run the Runge-Kutta method yet. I will do this here. The first thing we do is define our y dot as a function of time and y. Okay, notice that now this is actually a vector. So we have one element in this vector is our y2, and then the other element of the vector is this function, which comes directly from the equation of motion and is in terms of y2 and y1, as well as the function p, which is defined by the time interval that we're in. So this will be called every time interval to give us the y dot. Okay, once we have that function defined, and I encourage you to look at the documentation for ODE 45 to see exactly what the format of this function should be, but it must be in terms of a time variable and a response variable. That is how the function knows to call your response function. So we feed it that function, then we give it a time range and some initial conditions. That's all it needs. And then it returns a structure which we must again break apart to get our time vector. That is the x variable according to the result of the ODE 45 function. And the response u is the first element of the y vector. Remember that our y vector is both u and u dot. We only want the u in this case, so we pick the first element. And after that, we also generate a analytical function, which gives us our true value, and we calculate the mean squared error for the Runge-Kutta method as well. Let's look at what the Runge-Kutta response solution looks like. We notice a couple of things. First of all, the result is extremely good. If we zoom in, it's almost impossible to notice any sort of error in the actual calculated values. So this is a great sign. In addition, you'll notice that the step size is actually not constant. This is one of the sophisticated features in the built-in algorithm in MATLAB. In fact, it is the default feature. It is possible to implement Runge-Kutta with a fixed step size, but one of the major advantages is that it has the possibility for adapted step sizing. So if you notice, the function has small step sizes when there are large changes in the velocity. In other words, the displacement, the slope and the displacement is changing rapidly. In cases where the slope is basically constant, we see that the step size actually becomes a little bit larger. And so this is one of the nice features of the Runge-Kutta method. You'll notice that we've been calculating the mean squared error for each of these methods. So let's look at what that looks like with respect to our time interval delta t. This is the plot we have here. On the bottom we have the time interval, and on the y-axis we have the mean squared error. Notice that for interpolation in Newmark's method, as we would expect, the error gets lower as the time interval gets smaller. That is a common feature of all these algorithms. Of course, the Newmark near the right, the Newmark linear near the right side was unstable, so the error was much larger. But actually, as we get smaller in time interval, it actually improves upon the Newmark average method. We also notice that interpolation is consistently outperforming the Newmark methods. This is, again, has to do with the fact that this is a actual exact solution as long as the force can be described as a linear function. The Runge-Kutta method is this error is displayed simply as a line because we can't define a specific time interval for this method. We can, however, look at the minimum step size, which in this case happens to be around 0.04. So actually greater than the minimum step size that we used in this case for the other methods, which was 0.025. So in a sense, this is looking really good for the Runge-Kutta. Not only is it using adaptive step sizes, which reduces the overall number of computations that are made, but it's also getting much lower errors for somewhat of a larger step size. So overall, things are looking very good for the Runge-Kutta. Part of the reason here is that there's a lot more sophistication built into the function that MATLAB has implemented that we necessarily can do by hand in many of these cases. So it's possible to expect that some professionally coded Newmark's algorithm with more sophistication may be able to get close to the Runge-Kutta. But again, this emphasizes the fact that with Runge-Kutta we can take advantage of a lot of these built-in algorithms already to produce some pretty good results. All right, so let's summarize everything we've learned so far in one quick slide. We looked at 4 primary classes of numerical methods for estimating dynamic responses. The first was the interpolation or piecewise exact method. The principal assumption here is that the force is a linear function between time intervals. So this means that the method is, because it is an analytical solution under this assumption, it is exact given the assumption, which is a nice convenience because it means that the solutions are actually pretty precise when the assumption is not too far off. So in general, for linear systems, we found that it was a great choice. However, we do not have a good way to implement this for nonlinear systems. Nevertheless, for the linear system that we simulated in MATLAB, this method outperformed both variations of Newmark, so important to keep that in mind. Central difference was the second method we covered. Now, we did not simulate this method, and I do not recommend you spend a lot of time trying to understand it. Although it is a popular method, important to understand its context. It does not provide significant advantages over Newmark or the Runge-Kutta method. So we'll kind of keep it in the back of our minds. However, it's important to review the basic assumption here that it uses a set of 3 displacement points and calculates the central difference in order to estimate the velocity at the current time step and uses that to project forward. Okay, so the basic assumption. In this way, it is somewhat similar to the Runge-Kutta and Euler methods. However, it does also require an estimate for acceleration, which those don't. There are nonlinear and linear variations of the central difference theorem as well. Newmark's method has 2 variations, constant average acceleration and linear acceleration. These, as the name suggests, make assumptions about the behavior of the acceleration in between time intervals. It is possible to implement both of these for nonlinear systems, although we did not cover explicitly how to do that. but they also perform very well for linear systems. The constant average acceleration has the advantage that it is unconditionally stable. The linear acceleration has better accuracy for small delta t's. And finally, we covered Euler and Runge-Kutta methods. Now, Euler is a method that you necessarily wouldn't apply, but it is important to understand it because it is the basis for the Runge-Kutta method, which is the real workhorse in this case. And Runge-Kutta method had several advantages. It has an explicit solution for nonlinear systems, and in fact, we saw that you can formulate linear systems and nonlinear systems equivalently. It is also available in most commercial computational softwares, and this comes with added sophistication. For example, we saw that in MATLAB, this method by default runs adaptive step sizes. So in general, for single degree of freedom systems, I recommend that you use the Numerical and the Runge-Kutta methods. If you're dealing with linear systems, you can also use interpolation. For nonlinear systems, I highly recommend the Runge-Kutta method.